Okay, let's take a trip back in time, way back, before the internet as we know it even existed. Back then, your phone, your TV, and your computer, they were all on totally separate networks speaking completely different languages. So the big question was, what if? What if you could build one single universal network that could unite them all? Well, that was the absolutely massive, ambitious dream behind a technology called asynchronous transfer mode, or ATM. I mean, really think about that for a second. Before we just called everything the internet, you had the phone network, right? That was its own thing. Then you had a whole different system for TV signals and another one for computer data. They just weren't built to talk to each other. So the challenge facing engineers was enormous. How in the world do you build a single unified network that can handle literally everything? And that was the mission, the ultimate goal. Which brings us to our first section, the quest for one network to rule them all. The vision here, it was nothing short of revolutionary. We're talking about a single, incredibly powerful system that could carry every kind of information you can possibly imagine, all at the same time. But see, it wasn't just about mixing all that traffic together. The real trick was guaranteeing quality. A phone call can't have weird delays, right? And a video stream has to be smooth. It can't be all choppy and broken up. The network had to be smart. It had to be able to prioritize that super time-sensitive stuff over, say, a big file download that can take its time. That guarantee, that was the core problem ATM was designed to solve. So how did they tackle this massive challenge? What was the secret sauce? Well, that brings us to section 2, the ATM cell solution. And the answer was as elegant as it was radical. You take everything, your voice, your video, your data, and you chop it all up into tiny, identical, bite-sized pieces. This was the brilliant idea at the heart of asynchronous transfer mode. And, the whole solution is hiding right there in the name. Asynchronous just meant that speeds weren't rigid. Devices could actually negotiate how fast to talk to each other, which made the network super flexible. And transfer mode? Well, that's the big one. It points directly to its most important feature, using these small, fixed-sized packets called cells. And this is the heart of the whole operation. Every single ATM cell had this exact same super simple structure. You've got a small header, think of it like an address label, and then you've got the payload, which is basically the cargo bay where the actual data gets stored. And the magic number was 53 bytes. That's it. A tiny piece of a phone call, a fragment of an email, a single pixel from a video. It didn't matter what it was, it all got packaged into this identical 53-byte container. That standardization was absolutely key. So, of those 53 bytes, the first 5 were the header. This was the GPS for the package, right? It contained all the routing info, telling the network switches exactly where to send this little cell next. And the remaining 48 bytes, that was the payload. That's where the actual data lived. By keeping these cells so small and so uniform, the network could switch them around at unbelievable speeds. And this meant a single giant file transfer could never hog the line and block something more sensitive, like a voice call. It was incredibly fair. Okay, so let's just recap the core ideas here. ATM was built on a few key principles. It used those fixed-size cells we just talked about. It was connection-oriented, and we're going to dive into what that means in just a second. It could handle any kind of traffic you threw at it. It could guarantee quality of service, and it didn't even care if it was running on old copper wires or brand new fiber optic cable. This thing was built to be versatile. Which leads us to section 3, and a really important question. With all these millions of tiny cells flying around the network, how on earth did ATM make sure they all arrived in the right order? Well, the answer was a really clever concept called a virtual circuit. Now, this is a huge difference from the internet we use today, where data packets can take all sorts of crazy routes to get where they're going. ATM was what we call connection-oriented. Before even a single byte of data was sent, the network would figure out and reserve a specific, predetermined path all the way from the sender to the receiver. And this image here is the perfect way to picture it. That virtual circuit is kind of like booking a non-stop train journey. The track is reserved just for your train, which means all the cars are guaranteed to arrive together in the correct order. In the world of ATM, every single cell from your transmission followed that exact same path. No exceptions. And when you put them side by side like this, the difference is just crystal clear. ATM's virtual circuit is that predictable, orderly train journey. The Internet Protocol, or IP, which powers today's internet, that's more like a car using GPS in heavy traffic. Each packet is on its own, trying to find the fastest route at that very second. It's really flexible for sure, but it also means packets can show up all out of order and need to be reassembled at the destination. ATM's approach, on the other hand, guaranteed performance. Okay, so at this point, ATM sounds like a complete slam dunk, right? The undisputed future of networking. But, well, the story isn't quite that simple. As we'll see in Section 4, there was a massive gap between the incredible promise of ATM and the cold, hard reality of actually deploying it. I mean, just look at the promise here. On paper, this thing was a world beater. It offered the absolute best support for mixing voice, video, and data. It was super efficient with bandwidth. It had amazing quality of service for anything that couldn't handle delays, and it was scalable to speeds that were just mind-boggling at the time. It was perfectly positioned to unite everything, from your small office network to the global telecom backbone. But reality hit hard. For one, that 5-byte header on every tiny 48-byte payload, that created a pretty big overhead. Almost 10% of your bandwidth was just being used for addressing. People called it the cell tax. Even more importantly, ATM was expensive. It required a complete rip-and-replace overhaul of existing network hardware. And while ATM was struggling with these costs, a simpler, much cheaper rival, Fast Ethernet, was quickly getting good enough for most offices and homes. And so, this brings us to our final section, ATM's lasting legacy. Because even though you probably don't have an ATM port on your laptop today, and even though it lost the race, the core ideas behind it are very, very much alive. It's like a ghost in the modern machine. And here's the big twist in the story. ATM absolutely lost the battle for the desktop. Ethernet won that race because it was just cheaper and easier to implement. But many of ATM's foundational principles, they were so good, so powerful, that they ended up winning the war for the network core. They became the backbone of the modern internet and our massive telecom networks. And this quote really just sums it all up perfectly. That intense focus on quality of service, the whole concept of virtual circuits, the efficiency of switching small cells, these ideas didn't die with ATM. Not at all. They evolved, and they became essential parts of the DNA and the technologies that power our high-speed, always-on world. Its spirit is alive and well, managing the traffic on the internet you're using right now. Which leaves us with a really fascinating question to chew on. The story of ATM shows us that even a technology that doesn't win the popular vote can introduce revolutionary ideas that completely shape the future for decades to come. So what core concepts that we kind of take for granted today will end up becoming the hidden, essential building blocks of whatever comes next?